Hi everyone, I'm Stephanie from UC Berkeley, and today I'll be talking to you guys about our work on understanding and diagnosing visual failures in vision language models. So vision language models have been useful for lots and lots of tasks, especially ones that are reliant on the language model's expert level knowledge. But when it comes to solving vision-centric tasks, which we define here as tasks that rely solely on visual input and not on background knowledge or reasoning across text, these models do a lot worse. So one example of this task is multi-view correspondence, where given two images, the model's task is determine which multiple choice point in the second image corresponds to the reference in the first. And VLMs often get this task wrong and sometimes only achieve random chance performance, even though it has access to large pre-trained vision and language models. These results are especially puzzling when, on the other hand, evaluating just the vision models on multi-view correspondence, you find that they often do have the right representations to use. And by evaluating the vision models here, I mean that we're just taking the spatial feature maps, extracting the point for each multiple choice answer, and picking the answer with the highest cosine similarity. So it's a pretty simple process, but it still gets it right. So just to summarize this finding so far, moving from a visual evaluation strategy to a VLM evaluation strategy gives us two main observations. First, we have this global mean shift from, in this case, around 60 to 80% down to around random chance level accuracy. And two, we don't have a guarantee that the rank ordering of model accuracy is preserved. So this means that the best vision encoder for a task might not be the best vision encoder once it's used in a VLM. And the second point is really important because if you're using these VLM benchmarks as a more flexible way to evaluate vision models, you're going to get inconsistent results depending on how you decode these vision representations. Now, these results aren't entirely surprising. There's scattered evidence for this trend if you put together a bunch of papers that I've cited here, and these papers evaluate families of vision models and vision language models on these sorts of vision-centric tasks. But what we're doing in this paper is taking what we've learned so far and doing a more controlled study and analysis of why this is the case. So to run this controlled experiment, we use VLMs where only the vision encoder is swapped out and the language model is kept fixed. The LLM here is fixed as Vicuña 1.5, and we go through 4 different vision encoders. So one example of this is Dino V2 plus Vicuña 1.5. We also use VIT supervised on ImageNet classification, and we use 2 image text contrastive models, CLIP and SIGLIP. As an aside, for each of these VLMs, there's also a fine-tuning stage where the projector is fine-tuned to project the vision representations into language properly. So this lets us actually use all these different vision models and decode those representations. As a second aside, these models are from the Prismatic VLMs paper, which I've shouted out here, which trained them originally to study the axes of VLM design that matter. But for us, these models really let us evaluate VLM performance by varying the vision representations without changing anything about the VLM. So we don't have to change the architecture, the training data, or any part of the inference pipeline. In addition to this suite of 4 models, we also evaluated some common open source VLMs that also have this 3-part structure of vision encoder, projector, and language model. And for some of these cases, they also use out-of-the-box vision models like CLIP and SIGLIP, and for other cases like InternVL, the VIT is actually trained to be used especially in the context of their VLM. In terms of benchmarks, we choose 6 vision-centric tasks. So on the left, we have 3 correspondence tasks, which look similar to the multiple choice example that I gave at the beginning. They're from the Blink benchmark. And these test for semantics, they test for multi-view correspondence and robustness under lighting conditions, and also object affordance understanding. And then on the right, we also evaluate relative depth estimation, comparing art style, and also making inferences about 3D objects from limited viewpoints. So for each of these tasks, we have two evaluation strategies, one for the vision model only and one for the VLM. And I'm happy to go through all the evaluation and prompting details afterwards. We don't have enough time for that, but they're also all in the paper. So when we evaluate these four models on 6 benchmarks, we see two striking trends, which I alluded to in the beginning. First, for each task, as you move from the vision model evaluation to the VLM strategy, you get a mean shift downwards. And this, in most cases, this mean shift starts from some non-trivial accuracy and goes down to around random chance. And second, these lines don't maintain rank ordering of the vision models. So if you look at semantic correspondence here, even if Dino v2 starts out as the best vision model for semantic correspondence, it can suddenly drop to last place if the decoding of the vision representations comes from a VLM. We also see this story hold in 3 more commonly used open source VLMs. Now, depending on your background, your experience with VLMs, and which reviewer of this paper you are, this finding that VLMs have shortcomings in processing visual input can be either very obvious or very surprising. Either way, these results point towards something in the VLM that is not the vision encoder being a bottleneck in these tasks. And we're going to investigate 3 hypotheses around why this might be the case. A first very natural hypothesis is to wonder whether these vision representations are degrading after they come out of the vision model. You can imagine that the projection layer and the language model could be mangling the vision representations in such ways such that they're unusable, even if you have the right algorithm. So to test if this is true, we extract vision features after every layer of the VLM and run our visual evaluation strategy on them. So we're basically placing vision probes after every layer of the projector and after every layer of the LLM. This is around 35, 36 layers. And for reference here in the results, the gray portions are the results for the projector module, around 4 layers, and then the white parts on the right are the results for the language layers, around 32 of them. So looking at these results, as a whole, we don't really see a consistent dropping from vision encoder level performance down to random chance performance, which kind of tells us that the vision representations here are not systematically degrading throughout the VLM. There's a lot of interesting wiggling here that I think we can all hypothesize about and give our best guesses as to why this is the case, but at least for our purposes, we don't see this systematic degrading, so we're going to move on to our second hypothesis. So the second hypothesis was that the VLM's brittleness to its input prompt could be what's causing this problem. So to test this, we follow the prompt tuning setup from Lester et al. And basically, we prepend extra randomly initialized embeddings to the front of the prompt and then tune it on 1,000 few QA examples of the task. So in this case, the only thing that's changing is the prompt embeddings that we've initialized and put in the beginning of the original prompt embeddings. And then we can look at results. When we evaluate task performance across 1, 5, and 10 prefix embeddings, which are along the x-axis here, we can see a little bit, a marginal improvement when you add 1 embedding, but you start getting diminishing returns, and you even get worse performance as you do more prompt tuning, and in no setting do you even start approaching the performance of the visual encoders, which are the dotted lines. So this tells us that the VLMs are probably somewhat brittle to input prompt, and lots of papers around LLMs and VLMs have shown this, but this is not explaining why our vision representations are not being used properly. Okay, so ruling out the prompting and the quality of representations, we turn to the role of the LLM itself and how it uses the vision representations that are going into it. So here, for each task, we LoRa tune each VLM module separately on 5,000 examples of the task at hand. So this means, in one case, we tune the VIT and keep the projector and LLM fixed, and then we tune the projector and keep the VIT and LLM fixed, etc. And then before doing this tuning, we can preemptively ask, if we saw boosts in performance in each of these settings, what would that mean for us? And we came up with some of our own ideas of what it would mean. The first two we've already kind of shown evidence against. The vision representations are not too low quality, and the projector is not mangling the representations. So the third one is what we're really interested in seeing results for. And we get two sets of results. On the left, benchmarking on the same tasks as before shows us that the LLM-tuned module gives us the largest improvements over random chance. And on the right, I visualized a couple of attention maps where we took the LLM-tuned attention maps and subtracted out the original ones. So this tells us that given lots and lots of examples on these correspondence tasks, the LLM has learned to allocate more attention to the visual prompts in the image. And this is really exciting because to do these correspondence tasks, you need to be able to find and attend to the visual prompts and the little multiple choice labels before you can even begin to answer the problem. There are a lot more of both sets of results in the paper, as well as some analyses about how tuning the LLM best overcomes language priors. But overall, this experiment tells us that the most promising place within VLMs to start for improving vision-centric task performance is in the LLM and how it handles its vision representations. So all in all, going through these three hypotheses, this all leads us to say that the vision representations in VLMs can already do many of the vision-centric tasks that we care about, like correspondence or depth estimation or art style comparison. But for VLMs, these representations can often be hidden in plain sight. And with that, I want to give a big thank you to my mentors and collaborators, Tyler, Devin, and Trevor. And yeah, come say hi at Poster 12 today.
We have time for about 2 questions. So I'll ask questions. Stephanie, I'm curious. So Tom was just talking about some properties and some characteristics and observations about reasoning in VLMs. Do you think this kind of findings about the utilization of the visual encoder tells us something about these findings? Speculatively. Clearly.
Speculatively. So your question is whether these sorts of findings kind of might be able to fit into the idea of the jagged.
Yes, yes, especially in the VLM case. So we had a few cases at the end.
Yeah. Just off the top of my head right now, I think that solving this sort of problem and kind of a next step past this diagnosis would be a prerequisite in being able to fill in the jagged edges of AI. If you don't have VLMs that can process the vision inputs properly, then you don't have a model that can really take advantage of all the representations that it has and its sensory inputs.
Cool. And do you think that basically what you're pointing out to is that we should go more in the direction of pre-training kind of like diffused multimodality from scratch? That kind of connects to Luke's talk yesterday on the kind of different class of models.
Yeah. This gets at what comes next after this diagnosis. I think training some of these early fusion models, like the models that Luke talked about yesterday morning, could be a really cool solution. I think VLMs with tool use could be a really cool solution. So if the LLM thinks that it needs a segmenter or an object detector, but it can't do it itself, it can call upon this tool and solve the problem.
Okay, cool. Let's thank Stephanie again.